Okay, this is a follow-up to the demo that I just showed you. I want to show you some features in Logger Pro because in addition to calculating all these things behind the scenes, you can force it to calculate some of these things explicitly for you. So for instance, we know that slopes on velocity versus time, we know that that will give you acceleration. So I can pick an interval here. Just highlight an interval here where it looks like it's pretty straight and go over here and hit this button that will calculate a linear fit in that interval. And so you can see it's fit this black line, right, so that it fits the data that I highlighted, the interval of data that I have here where I picked out the flat line. And if I look at the slope value here, it's telling me it's 0.34 meters per second per second. So right away, the units tell me that it's an acceleration, right? If you ever get confused in all of these permutations of areas and slopes, right, the units can be your guide, right? So rise over run, the rise has units of meters per second, the run has units of seconds, so that's meters per second per second. So that's 0.34. Let's remember that number. Now let's go and do the trick where we can make it show us the acceleration over here. And let's expand this a little bit. We don't care about that big deceleration. So look at this area over here, the same area, right, that looked pretty flat, looked like a straight line over here, is giving us a relatively constant value. I can actually have it run statistics in that interval that I've highlighted. And it will tell me the min, the max, and it will tell me the mean. And look at the mean value here, 0.34, right? So the mean value of this noisy acceleration graph, which looks like it's roughly a horizontal line, is 0.34, and that is the slope down here of 0.34. Right? So that's a good trick if you're using Logger Pro to analyze motion graphs. The other thing, of course, this is slightly more sophisticated, but let's go back to our position versus time graph. If you don't know already, then it should be clear to you that this is not a linear graph, right? In position versus time, the slope is always changing because the velocity is always changing, right? When you have constant accelerations, these are the types of graphs you get. You get flat horizontal lines for acceleration, like so. Right? I mean, we have these spikes here, but you know the intervals of constant acceleration are flat. That's what constant graphs look like, which then gives you straight lines, right, of 0 and of this positive 0.34 and of 0 again. Gives you straight lines in velocity. That's what constant acceleration does. And then what does constant acceleration look like in position? I mean, if it's 0, it's boring. But if you have a constant acceleration that's not 0, then what you get is you actually get a curve, right? You have to get a curve because the slope has to be changing. And more specifically, it's a quadratic, right? So if I fit a quadratic to this interval, let's see if I forget if that's possible to do in one curve fit. Let me pick the quadratic function here. Try fit. Okay, so it has now fit a quadratic. You can see the black line continues out of this region here. So it fits the highlighted portion of the data really nicely. In fact, you can see it's a perfect quadratic. And then if you look at your equations of motion, right, this is a quadratic on position versus time. The position usually we're calling displacement is d. So we have a d is equal to at squared plus bt plus c. So what is this? If you look at the kinematics equation, its displacement is your original displacement, which would be the c value, that would be the constant value, plus velocity times time. So b would be your initial velocity. And the most interesting thing, of course, is the t squared term. If you look at the kinematics equation, it's 1/2 a t squared, where a is the acceleration. It's kind of unfortunate they're using the coefficient a here. That's a little bit confusing, right? Lowercase a for acceleration. The coefficient of t squared in the displacement equation for constant acceleration is 1/2 at squared. And they're saying the coefficient of t squared here is 0.17. So if I want to know what the acceleration is, I set 0.17 equal to half of a. Solve that for a, I get 0.17 times 2. That's 0.34, which of course is what we determined the acceleration to be, right? So we have here embedded the equations of motion, right? You get a quadratic function in time for displacement, a linear function in time for velocity, and the acceleration is a constant function. Okay, that's what I wanted to show you here.